Hi, Andrea. How are you?
I'm doing great. How are you, Chuck?
Well, fantastic. I love to, have you share a bit about yourself. So please tell us a little bit about yourself and why you're involved with SAIR's, foundation.
Sure. My name is Andrea Bertozzi. I'm an applied mathematician at UCLA. I've been working in many areas of applied mathematics over about 30 years of my career. The last, I don't know, 10 to 15 years, I've gotten very involved in machine learning and AI and how to take ideas from fundamental mathematics to develop very novel approaches for many real-world problems.
Very good. Well, one of SAIR's foundation missions is to bridge AI for science and science for AI. How do you think organizations like us can help drive meaningful progress?
Oh, that's a great question. Well, there are so many opportunities here on the interface between AI and science. We're in a situation where we've got people developing really novel ideas in the AI field as well as in science. And so now we're starting to see cross-fertilization between those areas. And I think what an outside organization like yours could do is to be able um, to get the scientists who are kind of in the trenches doing core science to learn more about what can be done in the AI sphere, and then the developers of algorithms, and that's more what I do, although I do some science as well, to be able to think about the science problems and how they fit into the AI world that they're developing. And I think that forming a bridge between these communities can make a big difference.
I love that because actually, if you use my Zoom, I would have the Golden Gate Bridge. That's my favorite bridge. You probably know, and
Beautiful.
it's bridging between academia and science, and industry, but
Mhm.
also the different generations of researchers. So with that said, how do you see the future unfolding at the intersection of AI and science?
Well, it's just an exploding area right now. I have had a lot of fun working in my own, spaces there. So, for example, we've been looking at some problems in DNA folding and design of single-stranded DNA aptamers. And that's a beautiful problem because it has a lot of fundamental mathematics that goes into the chemistry of how these things work. And at the same time, there's a very, very strong need for modern machine learning and AI methods to be able to partner with some of the fundamental chemistry going on in that problem space. That's just one area. Certainly, there have been huge strides in protein folding. So chemistry, I think, is a very strong area, but you can go all the way into lots of different areas of engineering. So for example, looking at engineering design, right, and getting AI to assist with that as well. These are just a few examples.
Well, I love it. From your work in mathematics and engineering, what do you see AI having the biggest impact on real life scientific problems?
Oh, I mean, the possibilities are really endless here. Um, I mean, what we're seeing right now is the ability of the AI to be able to automate what used to be very tedious analysis. And so I think what would be interesting to see is how far can we push AI to assist with the creative process of science. And I think we're already seeing that being developed in the area of foundational mathematics and AI being used to try to prove theorems in mathematics. But it would be really interesting to see how far this can go in lots of other areas of science.
Well, that's great. Well, I think you emphasize on developing interpretable tools that respect physical laws. How would you define interpretable here, and how does it differ from traditional black box machine learning?
Well, so interpretability is an important aspect to algorithm design. And so, we saw with the advent of modern neural network methods sort of an explosion of functional ability, and the interpretable understanding of what's going on kind of under the hood with these algorithms is now being further developed in that space. So I think that's great. I think interpretability is a moving target. And As a mathematician, I interpret interpretability as something that would involve being able to understand an algorithm at its fundamental level, to be able to prove things about it, and to be able to predict what it's going to do, at least at some theoretical level.
Very good. Well, how has the common language of mathematicians or mathematics enable you to apply fluid dynamics to fields such as DNA discovery? And what's the primary challenge in keeping these AI models physically interpretable?
Oh, that's a great question. Well, I think this is a very nuanced question with lots of examples. I'll just give you one example.
Please.
So one thing that I've enjoyed working on myself is taking ideas from surface tension in fluid dynamics, which is a very fundamental idea. And we have mathematical ways of representing that. And it turns out that mathematics has a parallel for looking at high-dimensional data on graphs. And I've really enjoyed taking some fundamental ideas from numerical algorithms for fluid dynamics and porting them over to AI and machine learning methods and seeing how they can really advance that field in a way that one would never, like a traditional fluid dynamicist from 200 years ago would never have even thought about.
Oh, that's an excellent example. And then my last question is, well, I think you have attempted to model social behavior with math. What do you think is the role of a mathematician when applying rigorous algorithms to issues that benefit society?
Oh, there are so many wonderful examples there. I think, as a mathematician, we're sort of trained to think in the clouds, but also keep our feet on the ground, right? And so we can use that same perspective to think about, how can we take these ideas and find novel benefits to humankind, at the same time be able to, to design, or at least to look upon these methods in terms of how do we safeguard humanity from possible negative effects while still taking advantage of the positive effects of these algorithms.